Today will be the first time that we follow the usual class schedule. So today we will go from 3:40 to 5:05, and then we will on Thursday we will go from 10:50 to 10:12. I announced this already on the first day, so you know on Monday there will be 5 minutes more, and then on Thursday there will be 10 minutes more, because you will have a two-week break during the semester. So we are still talking about convergence of series, and last time I introduced one of the tests, namely the so-called comparison test. Maybe I recall this. Okay, so this test is for series which have positive terms. So we have two series over AN and series over BN, and the essential requirement in this section is that AN and BN are both positive. So with AN larger than 0 and BN larger than 0 as well. Now, if we know that AN is smaller or equal than BN for all n, normally the series is starting from either 0 or from 1. So if this relation holds for all n which are large enough, so for some large n, then we have the following conclusions. So first of all, if we know that the series over Bn is convergent, then the series over AN is convergent as well. And if we know that the series over the AN is divergent, then we can conclude that the series over the Bn is divergent as well. Maybe I should stress once more, this is just useful if both series have satisfied this requirement here. So if all the terms are positive. If the terms of the series are not positive, we will learn different tests later on. So also if you, because this is already the second test which we have learned, the first one was the so-called integral test, and also for the integral test we had the same requirement. So it only works under the condition where all the terms are positive. So this is essential, and maybe just to remind you, what is the reason for this assumption here? Because whenever we talk about the series, then we want to understand, and if we want to understand whether the series is convergent or not, so what we essentially want to understand is whether if we sum up the first n terms, whether this sequence of partial sums is converging or not. Now, if the terms are all non-negative, then the situation is much more easy, or positive in this case. Then the situation is much more easy, namely, in this case, the partial sums, so this series here, Sn, this sequence forms an increasing sequence under this condition. Okay, and we know if we have a sequence which is already increasing, the only thing we have to prove in order to understand whether the sequence is convergent or not is we have to prove that the sequence is bounded from above. So in this case, the convergence behavior of this sequence is somehow more easy, because there are only two possibilities, either convergent or divergent. This is always the case, but for divergent there is only one possibility, namely that Sn tends to infinity as n tends to infinity. Okay, so the essential tool we have used here in order to prove also this theorem, or I demonstrated this theorem, I have proved it last time. The essential result which I need is the monotonic sequence theorem, and we saw this already also for the integral test. The essential result we needed in order to prove the integral test was also the monotonic sequence theorem. So this is an important theorem in this chapter. Now, last time I already discussed a couple of examples. In particular, I took all the examples which I considered already when I was talking about the integral test, and I showed you how to use the comparison test in order to derive the same result. So just to remind you, we looked at like series like this one, and also this one, where p is any real number. And last time I already showed you how to use the, so for those two you can use the integral test, but we saw that the comparison test is another tool. And for those two examples you saw the kind of the integral test is more easy, but for this series, which one? 1 over n to the cube plus n, we saw in this case using the integral test was quite tedious, because we had to replace this series by the integral from 1 to infinity dx over x to the cube plus x, and this integral is not easy. It's not so easy to compute. It's standard, but you have to do more computation. But using the comparison test here is clearly better than using the integral test. So in some cases it's better to use the integral test. In other cases it's better to use the comparison test, but roughly speaking, the comparison test is more stronger than the integral test. So the comparison test can, normally if you can use the integral test, you can also use the comparison test in order to derive the same result. Now, there are also examples where you cannot use the integral test. So what would be an example where we are not really able to use the integral test, and then we just have the only test which is left at the moment is the comparison test. Now, for instance, let's choose this one. Okay, so we have the series from n from 0 to infinity. Now, e to the n factorial. Now, the problem you have if you want to use the integral test is first you have to find a function f of x. So this is for the integral test, not for this one. First, you have to find the function f of x, and this function must have the property that if you evaluate it at positive integers or non-negative integers, what you get are the terms. Okay, so this is not so easy. The troublemaker here is n factorial. Actually, there are functions which you can choose, but we haven't explored such functions. So for such a series, we see it's not really possible to apply the integral test. So the natural tool, or the only tool we have at hand, is the comparison test. Now, how to prove or how to derive convergence or divergence of this series using the comparison test? Now, first of all, as I told you already previously, it's always good to first get a rough feeling or idea whether this series should be convergent or not. Now, for this series, it's very easy, because we know that n factorial converges, as n tends to infinity, converges to infinity very, very quickly. So this is also, we saw last time, functions like if you have a function e to the x as x tends to infinity will converge much more quicker than to infinity as any power function. Now, the same is essentially true also for the factorial. So the factorial, normally the factorial will be larger or equal than any power function for all n which are large enough. So this is somehow what you expect. But of course we have to make this more precise. But once you have found this observation that n factorial actually increases to infinity very quickly, you see that this will go to 0 very, very quickly, and you will easily get the guess that this series should be convergent. Now, so okay, what would be a good choice here for such an inequality? So we see, actually this is not enough. But n factorial, we will see an example, is even growing faster to infinity as any exponential function. Yeah, I should say a to the n. Now, one example is okay. for instance, we want to have that, or we want to understand whether n factorial is larger or equal than 3 to the n or not. Now, you see whenever you have something like this here, okay, normally you prove something like, if you are asked to prove something like this, you will prove it by induction. And for something like this, you will see that the induction step, because you can write this as n plus 1 times n factorial. And if you already know this, okay, then you see this will be larger or equal than n plus 1, 3 to the n. And now if n is large enough, then this n plus 1 will certainly be larger than 3. If n is larger or equal than 4, this is even already satisfied. So you will get that this is larger or equal than 3 to the n plus 1. So induction will work. But here this was just the induction step from n to n plus 1. What I have to verify is that I can also start the induction. And for starting the induction, you see that the n must be large enough. Because you see that if you choose, for instance, 0 is 1. Okay, and you want to have that this is larger or equal than 3 to the 0. This is actually satisfied. I shouldn't choose 0, I should choose 1. But if you choose 1, then you see this is equal to 1. But this is larger here, so this will not be satisfied. So you cannot. So this relation will not hold for all n larger or equal than 1. So you have to try. Okay, you try 2. So 2 is 2. It's larger or equal than 9. This is not satisfied as well. So I should maybe. Okay, and you go on like this. So then you have 3 factorial, which will be 6, which is larger or equal than 27, also this is not satisfied. Then 4 factorial, which is 24, is larger or equal than, now you have already 3 to the 4, so you have 1. Okay, this is not satisfied as well. Now we go on to 5, which is 120. Okay, and here you have 3, 21. Okay, this does not hold as well. So we have to go on to 6. Okay, and this is 720, which is larger or equal than, okay, now you see, okay, this is 9, this is 3, this is 6, okay. Which means, because I already showed the induction step, which means that this here will be satisfied for all n larger or equal than 6. Okay, so the crucial observation is that the induction step will go through once I have found the initial step. And for the initial step, I just try. Okay, any questions to this? Any mistake? Where? Okay, then this is, yeah, you're right, of course. Maybe we have got to go on to 7. Okay, so we are still unlucky. Okay, but it will work for 7 because you see you are now very close, and for 7 it will work. So you see that this relation is satisfied for 7. Okay, so but you see what is essential about this is that you will be able to use the same method to prove that if you replace 3 here by something different, 4, 5, 6, 7, okay, you will be able to do the same because you see easily that the induction step will go through no matter what you have here. Okay, if n is large enough, and then you have just to check, okay, till you find the first one, and then you can prove that also such a relation holds if you replace 3 by any number which is arbitrarily large. Okay, but this is not essential here. I mean, this is not essential for this series, but this tells you somehow that the growth of n factorial will be very, very quick. So as n tends to infinity, n factorial will tend to infinity very, very quickly. Now, how to apply this in order to figure out that this series is convergent? So you see that if you look now at e to the n over n factorial, Okay, and you plug this in here, then you see this will be smaller or equal than e to the 3 over n if n is larger or equal than 7. Okay, and you see that this series, that's why I chose here 3, because 3 is larger than e. So this series actually I can let the series start from 0. This series is convergent. Okay, now I can use the comparison test and I will get that this series is convergent as well. Okay, so you see that it's indeed possible to use the comparison test in order to figure out that such a series is convergent. Now you see, maybe let's look at one more example. So for instance, if we look at this, okay, so for instance this one. So again, we want to figure out whether this series is convergent. Now, we saw already the example where minus was replaced by plus. So in this case, we can easily use the comparison test, and we will see, and we can deduce that the series is convergent. Now for minus, actually, if we first use a heuristic reasoning, so you once more you see, if you look at the denominator, you see that n to the cube will be much larger than n. So as n is getting very large, you can actually forget about this here. So this series should behave, for n large, should behave the same as the series over 1 over n to the cube. But this series, we know already that this series is convergent. So we expect that this series is convergent as well. Now, how to reason in this case? When we have here plus, then it's very easy because we can easily find the lower estimate for the denominator, which will give us an upper estimate for the series. So just to remind you, so if you have given not this series but this one, okay, then n to the cube plus n is larger or equal than n to the cube. So you see that this term here will be smaller or equal, or this series will be smaller or equal than this one. Okay, and this one is convergent, so this one will be convergent as well. Now, you see here it's a little bit more complicated because the problem you have is that you have here a difference, not a sum. Now, in our textbook, you find a similar example. If I remember correctly, it's 1 over 2 to the n minus 1, and the textbook uses this example to motivate that we need a new test. Actually, I think this is a little bit deceiving. It's not the right thing to write something like this, because for if you use the usual comparison test, it's also easy to prove that this series is convergent. It's not complicated. You just need a suitable upper bound for n, but you will easily realize that n is smaller or equal than this one for all n larger or equal than 2. Okay, so you see that n to the cube minus n will be larger or equal than n to the cube half. Okay, so you will see that this series is smaller or equal than this one. But this one is convergent, so this one will be convergent as well. Okay, so if you read in our textbook, okay, our textbook is using such an example to tell you, okay, you cannot easily apply the original comparison test, so we need a new one. This is not a very good way of writing it, okay, because you see this is also for such, it's not complicated, but it's not a natural way to prove that this series is convergent. The more natural way is the observation I made before, so you can, because you can replace this, okay, or you can forget about this. So this series should behave the same as the series 1 over n to the cube. Here you use something different, because here you use the series 2 over n to the cube, twice this series. It's not so natural. Okay, so you see that there should be another result, okay, which should tell you because the series over 1 to the n to the cube is convergent, so this one should be convergent as well. This would be more natural. Okay, and this is the so-called limiting comparison test. I think the book calls it limit comparison test. Okay, so the situation is pretty similar as the situation we have discussed in the usual comparison test. So we have given two series convergent, and the terms are all positive. Okay. Now what you look at is the following limit. So the limit an over bn as n tends to infinity. If this limit exists, is equal to c and c is larger than 0, then this series is convergent if and only if this series is convergent. The other one is convergent. Okay, so you see that this obviously applies to this series here, okay? Because once you know this, you will define, so you call this here the series over an, you will define bn as 1 over n to the cube, and you see that the limit, because an is 1 over n to the cube minus n, bn is 1 over n to the cube, so the limit is equal to 1. So you see that the series over 1 over n to the cube and this series must have the same convergence behavior. If one is convergent, then so does the other as well. And this is kind of more natural than the reasoning I just used. Okay, so using the previous comparison test in order to figure out that this series is convergent. And actually, this is a quite powerful tool, because this tells you that what I used already several times, namely that you observe that n to the cube as n tends to infinity much quicker than n, so you can forget about this. This result makes this kind of reasoning precise. Now, you see, one thing you have to observe is that the limit must be larger than 0. This is important. Existence and larger than 0. Now, maybe let's look at the proof, because this is a good application of the monotonic sequence theorem, or actually what we use here in order to prove this is just the original comparison test. So first of all, because you have this condition here, so you know that the limit exists and is larger than 0, we know from the definition of the limit, this will imply that there exists a small m and a large m, where this small m is larger than 0, such that this inequality will hold for all n large enough. This is essentially what you see here is just a definition of the limit. So because this tells you that the limit converges to something. So here you have 0 to something which is positive. So if you fix a small enough epsilon interval around C, which will not, such an epsilon interval will not contain 0, and from a certain from a certain n on, all the terms of the sequence must be inside this epsilon interval. This is just the definition of the limit. So you see that this relation must hold if n is large enough. Now, you see that, okay, this means that an is larger than m times bn and smaller than large m times bn for all n larger or equal than n. Okay, and now you see already how to argue. For instance, if the series over Bn is convergent, then because of the original comparison test, the series over An is convergent as well. If the series over Bn is divergent, you use this inequality. If the series over Bn is divergent, you see that the series over An is divergent as well. So the series over the An and the series over the Bn have the same convergence behavior. Okay, so from this, the result follows trivially. So you see that actually this is just an application of the original comparison test. You also see why this condition is important here, because if this is equal to 0, then you still have an upper bound, but you do not necessarily have a lower. You do not find this lower bound, not necessarily. So if this limit is equal to 0, then you just get the upper bound. And if you just get the upper bound, okay, you just get this part of the inequality. You see that one direction of this theorem, because this contains two directions from here to here, from here to here, you see that one direction of this theorem is still true if the limit is equal to 0, if c is equal to 0. Namely, if you know that the series over the Bn is convergent, the series over the An will be convergent as well. So actually, you can extend this result. So if the limit is equal to 0, then the convergence of this series will imply the convergence of this series. And there is one more solution. There is one more situation, namely if c is equal to infinity. So if this limit is equal to infinity, then you see you just get the lower bound. Okay, so you see that you just get this part of the chain of inequalities. So you see that if c is infinity, then and you know Bn is divergent, An will be divergent as well. Okay, so you have also those two cases which in those two cases the limit comparison test applies as well, but just one of the directions will be true. Okay, so maybe I formulate this also as result. Okay, yeah. Again, if you have two series, the series over An, the series over Bn, with An, Bn both larger than 0. Okay, if and we assume again that the limit An over Bn as n tends to infinity equals to c. Now, if c is equal to 0, okay, so this case, so in this case, if you know that this series is convergent, then this series will be convergent as well. And if c is infinity, and you know that the series over Bn is divergent, then the series over the An will be divergent as well. Okay, but in those two cases, in comparison to the limit comparison test which you find in our textbook, so in those two cases, the other direction, you can easily find, you can try to find on your own, find an example for the first case where this here does not imply this. And try to find an example for the second case where this here does not imply this. It's actually one of the exercises in our textbook. Also to prove this here is one of the exercises in our textbook, but a very easy one. Okay, so any questions to this? Now you see that this is really a powerful tool, so the limit comparison test, because now you can argue very quickly that some limits or some series are convergent or not. So for instance, if you look at this series, n squared plus 1 over n to the cube minus 1. Okay, if you look at this series, now it's very easy to find this. So this is the series over an. You have to find a bn, but you see that the way you find bn is okay. You say that if n is very large, this will be much larger than 1, so you can forget about this. This will be much larger than minus 1. You can forget about this. So it's 1 over n. So in the limit, this term and 1 over n should have the same behavior. So you will define bn as 1 over n, and this here is then the sum of the series over an, and you see that an over bn. If you take the limit as n tends to infinity is equal to 1. Okay, so you can immediately apply the limit comparison test, and because the series 1 over n we have identified already as a divergent series. Okay, so this one is divergent, so you immediately get that this series is divergent as well. Okay, so you see this tool is very powerful. Okay, so for instance, one more example. Okay, so for instance, this one. Now, once more, having this tool at hand, this is very easy for this series to determine whether the series is convergent or not. You just use the same reasoning. So as n is getting large, you can forget about this. You can forget about this. Or let's choose another one. Let's choose this one, because this one is more easy. Let's choose this one. Okay, so as n is getting large, you can forget about this. You can forget about this. So you see that the series roughly behaves like this one. Okay. Now to make this precise, you define this here. You call this here an. You define bn as 2 over n log n, and you easily figure out. Because the reasoning which I just told you precisely means that this limit here is equal to 1. Okay, so you just have to, this means you can reduce this series to this one. You just have to understand the convergence behavior of this series, and you can immediately draw a conclusion about the convergence behavior of this one. But this series, we already discussed it previously, so this series is divergent. So this series is divergent as well. Okay, you see, now with this kind of tests, which we have developed at far for quite a lot of series, it's already quite trivial for us now to understand whether the series is divergent or not. Okay, it's just a matter of applying the tests. You see once more that if we once more look at this example here, the example I discussed previously. Okay, so for this series, we can apply the comparison test. I just showed you how to apply it. But here the application is not complicated, but at least you need some ideas. We will later on develop other tests which will help us for such a series to understand much more quicker whether the series is convergent or not. Because we are discussing quite a lot of tests, okay, and I know normally that students are quite confused. Why do you need so many tests? Now, some of the tests, like here, like the integral test, does not apply to such a series, so it's not convenient here. So normally, for a given example, normally you can choose lots of different tests, and many of them will work, but you still have to. So all of the tests have some advantage, okay? And like the comparison, the advantage of the comparison test compared to the integral test is much more easier to apply, Okay, we saw this for this example here. So for this one, 1 over n to the cube plus n. So for this example here, we were able to derive that this series is convergent by using both the integral test and the comparison test. But the comparison test much more easier. In particular, the limit version of the comparison test, because for the limit version, you just observe that this series is convergent. That's it. Now, for the integral test, we had to it's not complicated, but we have to compute a more complicated integral, which involves much more computations. So you see here, obviously, looking at this example, you see obviously the advantage of the comparison test. So the most important thing you should understand here in the section about integral test, comparison test, and then later on different tests, you should understand what is the advantage of one test over the other. Once you understand this, it will be very trivial for a given series to find whether the series is convergent or not. Now, let's stick once more to this example. So for this example, we could derive that the series is convergent. I told you already previously that finding the sum is a much more complicated problem. So for instance, for this series, okay, what is the sum is a very complicated problem. The only thing we can do so far is estimating the sum by using the most trivial method, which is to take the first few terms, to compute the sum, and take this as an approximation for this series here. And as I have explained previously, what we need always is an estimate for the error. So let's spend a few minutes to ponder about estimating sums or series. It should be sums of series. Now, okay, so if we have given a series, this is as I have explained previously, what we will do is we will take the first few terms, say the first n terms, and we will compute this here instead of, because we are not able to compute the sum here or the value here. So we will compute this here instead of this one and take this as an approximation. And what we essentially want to understand is the error. So what we want to know is, okay, if this here is equal to s. Okay, so what is the error? So the error is an plus 1 plus an plus 2 plus and so on. Now, if we have used the comparison test, then normally we have compared the given series with another one. So if we have used the comparison test, we normally have found something like this here. Let's say for convenience, for all n larger or equal than 1. So we have also a second series, namely this one. And let's denote by Tn the partial sums of this series. Okay, and again we have an error, call it Tn, which is now T minus Tn. Okay, now from this inequality we obviously get that Rn is smaller or equal than Sn, than Tn. Because this holds in the limit, okay, so actually this holds for every term, and if we take limits, it also holds in the limit. Notice that if I have here something like this here, this is not true. Okay, we have discussed this already last semester. Okay, because this is in the limit. Now, normally, because we have used the comparison test, so normally the Bn will be much easier than the An. That's why we have used that. That's why we have replaced the original series by this one. And quite often we can say something about the error of Tn. Okay, and whenever we can say something about the error here of about the size of Tn, we can use this in order to understand the error here of the original series. So in particular, if you have used, because normally what you use for comparison are either, so we have a few series which are very important and which we always use as toy examples. One class of such series are the P series. so 1 over n to the p, the series over 1 over n to the p, and the other one is geometric series. Now for the p series, we can compute here, we can estimate the error by using the tools we have seen in the last lecture. Namely, if you have a p series, because for a p series we have used the integral test, so you will be able to approximate this error by the integral, by the corresponding integral. If you have used the geometric series, then it's even more better, because for a geometric series, it's trivial to compute the Tn. So in both cases, you will be able to say something about the error. And this is important because you just compute this here, you get an estimate, you know how large to choose the n, such that you get an approximation of S up to a certain precision. So for instance, if you look at this series here, and you are asked to find the value up to a certain precision. Okay, what you will do is, okay, you use this here. So we have observed that 1 over n cubed plus n is smaller or equal than 1 over n cubed. Okay, so if you do approximations, then the error Rn will be smaller or equal than the error Tn if you use this series instead of this one. The series over this sequence instead of the series of this series. And you see that because this is a p series, so you can use the integral approximation. So this will be smaller or equal than the integral from n to infinity dx over x cubed. Now you see, okay, this you can compute in this case, so 1 over 2 n squared. And from this you will know, okay, how large you should choose the n such that the Rn is precise up to a certain precision. The rest is easy. You use either a calculator or a program like Maple. And if you want to have, if you use Maple, you can compute the value of this series precisely up to a precision you can choose on your own. So if you want to have the first 10,000 digits, no problem for Maple to compute it. And this kind of, in some sense, solves the problem of getting the value. But what we, of course, would like to have is a nice expression and not just a numerical value. Okay, so you see that also estimating the sum of the series is here possible if you have identified a series as being convergent by using the comparison test. Because normally the series with which you compare will be much more easier to handle than the original one. That's why you use this series for comparison. Okay, so any questions to this? Okay, so up to now we have discussed two important tests, the integral test and the comparison test, and both of these tests applied for series with positive terms. Now what we want to do next is we want to turn to the general situation where an is not necessarily positive. But first we want to discuss a more easy special case of the most general case, or of the case where you also allow that an is negative. These are so-called alternating series. Now, what is an alternating series? The most famous example is this one. You see that, okay, an alternating series is a series where the terms alternate between being positive and negative. So you see that either the first term starts with positive, then the second negative, positive, or the other way around. So in this case, you can write this as the sum of the series n from 1 to infinity minus 1 to the n minus 1 over n. Another example. For instance, minus. Okay, Okay, so if you look at this one, so this one starts with something which is negative, then positive, negative, and so on. So here you have minus 1 to the n, and then you see that the law how the terms are built is easy n over n plus 1. Now, what we essentially want to understand is the usual question. So given such a alternating series, so given a series where the an is minus 1 to the n minus 1 bn, and bn larger than 0, or where an is equal to minus 1 to the n bn, and bn is larger than 0, this is the same situation. You just take out the minus, you will get, you will arrive at this case here. And what we want to understand is, what we want to understand is under which conditions is such a series convergent. And this is a very easy case. We will see there is a very convenient result which allows us to derive very quickly whether such a series is convergent as well. You see, if you look at those two examples, okay, this example might be convergent, but this example is certainly not convergent. Why? What is the reason why the second example is certainly not convergent? Who knows the answer? Right, because this sequence does not tend to 0. In particular, this sequence is not convergent. Okay, it's not even convergent. So if this sequence is not convergent, okay, there is no chance that the series is convergent. Okay, and in particular, it does not get small. Okay, so what you add if n is very large is something which is too large. Okay, so for this series, it's very easy. For this series, you see that the terms as n is getting large, as n tends to infinity, tends to 0. Okay, so this series might be convergent. Now, there is a very, very easy test, which is called the alternating series test, or sometimes also called Leibniz test, because it's the test is due to Leibniz. And such a test tells you, okay, that obviously the first condition you need is that the limit of Bn as n tends to infinity, so here the Bn, the positive terms are 0. This is obviously a condition you need. And this simple test tells you one more condition, which is easy to verify, namely that Bn is larger or equal than Bn plus 1. Okay, so the sequence of Bn is non-increasing for all n. Okay, if you have those two conditions, then the series over the an is convergent. Okay, so this is a very easy criteria. Okay, so using this criteria, we can immediately deduce that this series is convergent, because you just look, you drop here this part here. You have just the part 1 over n, and 1 over n is a sequence which tends to 0 and is non-increasing, and that's enough. Okay, so it's, you see, for alternating series, it's very easy to figure out whether they are convergent or not. Now, the reason why such a simple result holds for alternating series is very easily explained. Namely, okay, so what I do is I draw the terms, I draw the partial sums. So what I draw is Sn is equal to the sum I from 1 to n of the ai. Okay, so you see for the first one, you see the first one here is positive if I choose the sign like this. So you see we start at 0. Okay, and the S1 must be larger than 0 because the first one is positive, and this length here is B1. Okay. Now the B2, so we see that, okay, so the S2, you see, if you look at the second term, A2, the second term is negative. So now you have to subtract from S1 B2. Okay, but you know that the first thing you know is that the sequence of Pn is getting smaller, and you know that you have the property of non-increasing. So if you draw the P2 here, the P2 will not be longer than the P1 because of this condition here. Okay, so maybe you end up here. So this is P2. Now for the next one, for the P3, you add again. And again, what you add, so this length will not be longer than the length of P2 because of this condition here. Okay, so you have something like, here's S3, and then you go here to S4. So this is P3, this is P4, and then you go here to S5, and this is B5. And you see that what I use here as well in order to draw this is that the sequence of Pn will go to 0 as n tends to infinity, which means here the lengths which you see here getting smaller and smaller. So this is this condition here. And you see already here from this picture that they will meet somewhere in a point, and this point will be the sum of the series. Okay, so this roughly explains why this result holds. This is of course not a proof, but you can already from such a picture you can easily figure out how to prove this result. Namely, if you look more closely at this picture, you will observe that, okay, if you look at Sn, where n is even, okay, so if you look at the even ones, where n is even, you see that the even ones should increase. And you see if n is odd, okay, the odd ones decrease. Okay, so this already gives you an idea how to prove this. Namely, you prove that Sn, as n is even, is increasing. This is the first thing you prove, and you prove bounded from above. Then you can deduce that the even ones, that Sn where n is even, converges. Then you just have to prove that the odd ones have the same behavior and they converge to the same limit. Now, okay, so we claim that the even ones, so this sequence is an increasing sequence. Now this is easily proved because, okay, let's look maybe at the first one just to get a feeling. Okay, so the first one is B1 minus B2. Okay, so this is larger or equal than 0. Okay, now let's look at S4. So S4 is certainly S2, okay, plus, and then B3 plus minus B4. Okay, but this one is getting smaller, so this will be larger or equal than S2. Okay, so S4 will be larger or equal than S2. And this already gives you the idea. Okay, so if you look at S2n, you can write this as S2n minus 2. And what you are missing is B2n minus 1 minus B2n. But this here, again, because of this property, it's larger or equal than 0. So this will be larger or equal than Sn minus 2. Okay, this proves already the induction step. So you see from here, okay, you get the conclusion. So S2n is increasing. Now, so this was the first step. So this is the first claim, claim 1. Now claim 2, S2n is bounded. Also, this is quite easy. You just group the terms now different. So here, if you see this here, we took out the last two of them and observed that the last two are larger or equal than 0. So we always took two of them. Okay, starting from the very end, we took two of them. But now we do it a little bit different. Namely, you observe that S2n is equal to, so you start with B1, then you have minus, and then you write B2 minus B3 minus, and then you have B4 minus B5, and so on. So the last one minus, you have one which is B2n minus 2 minus B2n minus 1, and then you have a minus B2n. Okay, you observe that, again you use this property, you observe that what you see in the brackets is again larger or equal than 0. And this last one is also larger or equal than 0. So it's from this, it's trivial that S2n is smaller or equal than B1. Okay, so you see that indeed this sequence is bounded. Now, from those two properties, you get that inducing the monotonic sequence theorem, you get that S2n is convergent. Okay, and now the rest is easy because S2n plus, so we get that the limit of S2n as n tends to infinity exists, and let's say it's equal to S. Okay, and now you just look at the limit n tends to infinity S2n plus 1. You want to understand whether this limit exists or not, but you easily observe that this can be written as S2n plus the last one, P2n plus 1. Okay, so you see that because this limit exists, and this limit exists because of this condition here. So you see that what you get here is S plus 0, so it's equal to S. So also the odd ones, so the odd index ones, the sequence of the odd index ones converge and converge to the same limit. And it's an exercise in our textbook to prove that, so you find this in one of the exercises to prove that if you have a sequence such that if you look at the subsequence where you just consider the even index, if this series is convergent, and if you look at the subsequence with just the odd index, if this sequence is convergent as well, and both converge to the same limit, then the original sequence is convergent and converges also to the same limit. So from this here, you can conclude that the sequence Sn is convergent and converges to S as well. And this actually finishes the proof of our result. So you see that the reason why I tell you this proof here is because it shows you once more that the essential tool we are going to need, or we are going to use in order to get a conclusion, is the monotonic sequence theorem. So everything we have discussed so far is based on the monotonic sequence theorem. This is our most fundamental result we have seen in this lecture so far. Okay, so any question to this? Now this is obviously a result which is very easy to apply. So maybe let's look at one or two examples. So for instance, if you have given this one, minus 1 to the n minus 1. Just, 2n over 4n squared plus 1. So for instance, if you look at this example, okay, so the question, of course, is whether this series is convergent or not. So what you're going to do is you will apply this result here. You see that the first condition, So the p end is this here. So the limit as n tends to infinity 2n over 4n squared plus 1 is easy, is equal to 0. So the first condition is okay. Now for the second condition, okay, what we have to prove is that 2n over 4n squared plus 1 is larger or equal than 2n plus 1 over 4n plus 1 squared plus 1. Okay, so this is something we want to know. Now this is inequality you can prove directly. Okay, so you see that n times 4n plus 1 squared plus 1 must be larger or equal than n plus 1. I do not want to erase this result here, so. For n squared plus 1. Okay, so what you get is 4n to the cube plus 8n squared plus 4n plus 1 should be larger or equal than. So all of those inequalities are in question because this is what we claim. Should be larger or equal than 4n to the cube plus 4n squared plus n plus 1. Okay, so you see that you can delete this here. And you can regroup this. Sorry, this is an n here. So this is actually 5n. Or let's write it like this here. Okay, so you can regroup this to 4n squared plus 4n is larger or equal than 1. And so again, this is in question, but this is trivial here because this can be written as this here, and this is trivial. This is trivially satisfied. So again, this would be in question, but this is trivially satisfied. Okay. I just want to say that actually this is, from a logical point of view, this is not the way you are going to reason. The way you are going to reason is from here upwards and not the other direction. Okay, because logically you start here, this is true, and then you go on. Okay, you see that this proves that this sequence here is non-increasing, and of course this is not the only possible proof. You can also look at the function 2x over 4x squared plus 1 and prove by taking the derivative that this function is decreasing, is another, or non-increasing is another way to prove that this inequality here is satisfied. Just depends what you prefer. But this shows that both conditions of this test are satisfied, which means that this series here is convergent. Okay, so any question to this example? Now another possible example would be this one. Okay, so for which p is this series convergent? Also this one is not complicated. So in this case, if you look at the limit as n tends to infinity, minus 1 to the n minus 1, 1 over n to the p. Okay, so this limit does not exist. Okay, so you can, in this situation, you can immediately conclude that you have convergence, divergence. And if p is larger than 0, okay, so this is the remaining case. So in this case, you call this term here Bn. So you easily see that 1 and 2 are satisfied. Okay, so in this case, you have convergence. Okay, so it's very easy for this example to apply this test. You see, this test is very convenient because it's very easy. Okay, so from all the tests we have seen so far, this is the test which can be applied most easiest. But this test can just be applied to a special situation, namely to series which are alternating. Now, actually, an interesting question is the following one. There are two interesting questions. So the first one. So we have seen that this easy series here is convergent. So obviously by this test. Of course, a good question would be, okay, what is the value? Now, for this series, it's possible to compute it. But the computation is quite tricky. This is one of the examples in our textbook in this chapter 1.5. So what you do is, okay, so we know that if you look at the partial sums will converge, and what you want to find is the limit. So what you do is, the trick here is to look at the even ones. Because if you look at the even ones, here's 2n, sorry. If you look at the even ones, you can write them as follows. And this is the real trick in the proof. So you can write them like this here. But if you write them like this, you have counted some too much. Okay, so you have to subtract. You see that this would be okay for the odd. For the odd. If I is odd, this would be okay. For the even, but the even ones here are negative. Okay, so you have to, if you write this sum here like this here, you have to subtract twice the even ones. Okay, so you have to subtract twice the even ones. 1 over 2i. Now this is very fortunate because this tells you that this relation here is satisfied. Okay. Now, how to use this? Last time I showed you, maybe you remember, I showed you last time that if you take this sum here and you subtract ln of n, okay, so we saw last time this will converge to something which is called gamma. Now, this suggests that you subtract here ln of 2. So this suggests that here the limit is ln of 2. Okay, so let's check this. So if you have S2n minus ln of 2, okay, because you can write this as the sum I from 1 to 2n 1 over I. Okay, and now we rewrite this a little bit. We write minus ln of 2n. Okay, and then we have minus, and then we have the sum I from 1 to n 1 over I, and we subtract here minus ln of n. Now everything is okay. Okay, because here minus ln of 2n plus ln of n is minus ln of 2. And now as n tends to infinity, this here will go to gamma. This will go to gamma as well. So this goes to 0. Okay, so the limit here, ln of 2. So we know that this series has the value ln of 2. You see, but this is tricky. Okay, to find this, you have to think a lot to find such an easy way to compute this series here. But it's possible. This is quite remarkable for this series. We will later on, maybe in 2 weeks, we will have a tool which will tell us very easily that the limit, that the value of this series is ln of 2. And then you will see that this is really, really tricky. Okay, so any questions? This is one of the exercises. Okay, so if you look at chapter 1.5, one of the exercises, and maybe the last one is this one. So sometimes it's even possible to compute the sum. Now, another interesting question is, if you look at a result like this, okay, a good question is always, can you remove one of the conditions? Okay, I told you this one, you are not able to remove it. I mean, removing it such that the conclusion holds. If you look at this one, you cannot remove it, okay, because we know that because of the test of divergence, okay, this is something you need, that the series is convergent for the conclusion to hold. But a good question is, can you remove this one? Yes or no? I mean, this is a quite tricky question, okay? Because it's somehow, if you think a little bit about it, okay, you would say this condition should not be necessary, okay? Because if Pn tends to 0, okay, this means, like the picture I just draw, this means that this kind of distances which you saw are getting small anyway. So it doesn't matter whether you overshoot sometimes, as soon as this is getting small. Okay, so somehow, somehow one could believe that something like this is true. But because this is a classical theorem, of course, it's not true. Because otherwise, you could simplify this theorem by removing this condition here. Now, but whenever you have something like this, okay, what is a counterexample? Now, here it's possible. It's not so complicated to give one. So you choose something like this here. Let's say, so you obviously have to divide if n is even, if n is odd first, because those ones are positive. So if n is odd, we choose like, let's say 1 over n. Okay, and if n is even, who has an idea what to choose? I mean, sorry, this is maybe wrong. So if n is even, if n is 2k plus 1, what you choose is 1 over k. And if n is even 2k, what you choose is 1 over k squared. Okay. Now why? So you see that an is 0. Okay, no problem. If you check this, actually, sorry, here I have a minus. So from this you see that the limit over Pn certainly is 0 as well. Okay, but what you see is that if you define Pn, so your Pn would be now the same definition but no minus here. So the Pn is not does not satisfy this property, so it's not non-increasing. Okay, and you see that you can this sum here, okay, in this case it's like this one. This is not really true here, so maybe I write here something like, I do not write the equality, okay, so it's 1 over k minus 1 over k squared. Okay, but you see that if so if this series you should not see this as equality, but kind of. Okay, so if you plug this in here, you could write this one as this one. But what you need for something like this, so plugging this in and then writing this is equal to those two here. So here you just divide into those two cases. Okay, what you need is that this series is convergent in order to say, okay, this is equal to this one. Otherwise, you're not allowed. It's not necessarily true, as I emphasized last time, that the series over an plus bn is equal to the series over an plus the series over bn. You need an assumption, namely that both of the series are convergent. Now here you see that this series is divergent. Okay. So now the way you argue is indirect. You say, okay, let's say this series is convergent. Okay. But if this series is convergent, you can add this one because it's convergent as well. What you get is this one, and you would get a convergent series. This is wrong. So from this, you see that this series must be divergent. So you have here an example of a series which satisfies one, but the conclusion is wrong. Okay, so this means you cannot remove this. Also, this is one of the exercises in chapter 5.1. Any questions? Now to finish this, let's also, this is something we really need later on, so let's ponder on again on the question of estimating sums. So assume that we have given alternating series, so an is equal to -1 to the n-1 bn, and bn is larger than 0. Assume that the series is convergent, so assume that the two conditions of the alternating series test are satisfied. The question is, okay, if you look at the error by approximating, so we know that this is now equal to s, by approximating s by the partial sums, okay, is there a good bound for this? Now, if you look at the absolute value, actually there is a very easy bound in this case, namely this is smaller or equal than bn plus 1. Okay, so this means that also this makes the situation very, very simple. This means that if you use this here in order to approximate s, then you can bound the error by the first of the bn you drop. Okay, will be a bound for the error. This is a very good bound. Now, the proof of this is essentially already contained in the picture I showed you when we started to talk about alternating series. So you have this kind of picture. So here you have B1, here you have S1, here you have B2, here you have S2, here you have B3, here you have B4, and you go on like this. So you see, for instance, if you take S1 as the approximation, okay, then you see that because your S will be somewhere in this interval, so the difference of S minus S1 will be at most B2, the first term you drop. And the same reasoning in general. So you see, this is very good because this tells you that, for instance, one series which we have not discussed, but which is alternating as well, and you see that here you have 1 over n factorial. Okay, so 1 over n factorial obviously satisfies those two conditions. So this is a convergent series. So if you want to understand, okay, if you want to compute the value of this series, okay, up to a certain precision. So for instance, you want to make the error smaller than for instance, find the first 3 decimal places of the sum. Now the first thing you have to understand, okay, roughly where is this, where is the sum? If you do some simple computations, you will see it should be smaller than 1. So in particular, if you look at this error estimate, you will see that the error is very simple. It's smaller or equal than 1 over n factorial. And this is something which, n plus 1 factorial. And this is something which tends to 0 very quickly. So you just have to check, okay, for which n will this be small enough, smaller than 0.0001. Okay, and if you do this, you will find out n is equal to 7. Yeah, for n is equal to 7, this will be small enough, and in this case, the approximation which you get. So what you have to do, is you have to replace here this series by the first 7 terms. You have to compute the first 7 terms, and what you get then is 0.368. And this will be a good, and those 3 digits here will be correct. Okay. If you want to have more precision, you maybe have to compute more. Maybe already from high school you know what the real value is. The real value is e to the minus 1. This is something we will also prove very easily, or which we will see later on. Okay, so later on we will be able to compute such sums of such series in a quite straightforward manner. Okay, so any questions? Now, next time I will, because so far we haven't tackled the most general problem, namely given a series where an is, we understand very well by now the case where an is non-negative, positive, or non-negative, doesn't matter. So this case we understand very well, and here we also understand very well the case where the terms are alternating positive and negative. So those 2 situations are not so complicated. So next time we will tackle the most general problem, namely given the general series where the an can be positive and negative, and the pattern is not necessarily like this here, so regular. And we want to try, and the question is the same. We want to try to find some tools in order to figure out whether such a series is convergent or not. Okay.